everyone. This video is going to cover the section 3.3 of your book. The section is current flow in semiconductors, and the two important concepts or the major concepts of this section are drift current and diffusion current, and it's very important that you guys know the difference between the two. So for drift current, I have a definition right there. It exists when an electric field is applied to a piece of semiconductor. So what does that mean? Let's look at this picture right here. We have that the black box is a piece of semiconductor. It could be silicon. And across it, we're applying in blue a voltage. So this being the positive side, this being the negative side, we know that an electric field is going to be created from positive to negative. So we have that an electric field flows here from positive to negative in this direction. One other thing that we know is that electrons flow in the opposite direction as the electric field, or towards the positive side. So we're going to have electrons going in this direction, electron flow in that direction. On a similar way, we have that holes flow on the same direction as the electric field. So holes are going to flow in this direction, like that. And we know that as a convention, we always take that electric current flows on the opposite direction as the electron flow, so the overall current flows in this direction. And the very important thing to know from drift current is that it is created by an electric field. So now let's look at the formulas for this drift current. First we have here J. J is the current density. Current density is current per unit area. So if you wanted to know the current, that is that is current is equal to current density times the area. And this is cross-sectional area, so it should be the area of this side of the semiconductor, for example. So we have that the total current density is equal to the whole current density plus the electron current density. And that can also be expressed as Q, which is charge, times the hole concentration times a new concept, which is mobility of holes, plus the electron concentration, the mobility of electrons, times an electric field. Well, this right here is electron charge, and we know that it is 1.6 times 10 to the negative 19 coulombs. We know, and we know the rest except for mobility. What mobility is I have a definition right here. It is the degree of ease by which carriers move through the crystal. So what does that mean? It's how easy these carriers, electrons and holes move in the crystal. And that is obviously material dependent. For example, for intrinsic silicon, you have that the mobility of holes is equal to 480 centimeters square per volt second. And the mobility of electrons is equal to 1350 centimeters square per volt second. So this is for intrinsic silicon, and we notice intrinsic silicon, and we notice that the electron mobility is greater than the hole mobility. And another important thing to notice is this electric field. And always remember, drift current is the one that is related to an applied electric field. Another important thing that you guys may need to know from this is sigma. Sigma is the conductivity and is equal to the charge mu p plus n mobility of electrons. So the very first part of our previous equation right there is equal to conductivity. So this sigma right here is conductivity. So we have that another way to express the current density is sigma times the electric field, Or, as you guys may know, the inverse of sigma, or the inverse of conductivity, is resistivity, which is this rho. So rho is resistivity. Okay, and that's basically what I have for from drift current. The most important thing, again, is that it is created by an electric field. So now we can move to diffusion current. Diffusion current at the beginning is a little bit more tricky, but it's not that bad. So we have a definition right here. What is diffusion current? It is the net flow of charge generated from carrier diffusion. So I have, what is diffusion? Diffusion of carriers of electrons and holes occurs when the density is not uniform. So let's take this example on the image on the left. So we're supposed to have a container with water. So we have different densities. We have more water, a high concentration of water on the left side, and a lower concentration of water on the right side. So if we were to have, or to remove, this barrier right here, we're going to have a flow of water from the higher concentration area. Let me try. From the higher concentration area to the lower concentration area. So we have water flowing here. So that's an important thing. The diffusion goes from the high to low concentration. And a similar thing will happen if we move to a piece of silicon. Let's say in this piece of silicon that you guys are somehow applying holes here to the left. Let's start with holes. So we're applying a bunch of holes. I'm going to put them as H+, H+, H+. So we are increasing the hole concentration on this side of the semiconductor. We're increasing this, and we obviously had some inherent holes that were part of these before, where you have a higher concentration on the left than you have on the right. So your holes, due to diffusion, are going to move from the left side, the higher concentration area, to the lower concentration area. So that's one important thing to notice, that carriers move from high to low concentration due to diffusion. So that is what is happening, and we can express that is expressed on a formula like this. The current density of holes is equal to minus, and we're going to talk about that minus in a little bit, times the charge times this new constant and this. I'm going to talk about all this in a bit. So this part right here is a material dependent constant called diffusivity. And that's a constant that's material dependent. And this little guy right here is the carrier concentration gradient. And I'm going to explain both of those and why this negative value is there. So let's start with the gradient concentration. So if we were to look at this picture and translate it into a graph, we will have something like this. So here on the left, we have P, which is the concentration of holes, and here is just X, the position. So on the left, you have a higher concentration than you have on the right, and that's expressed by that curve on green. So what the carrier concentration is basically the gradient, with that is the slope of this curve right here. So you have a slope like that. And we know that when the slope is in that direction, that is a negative slope. So if you have this value right here be negative, your overall current will be on the positive X direction. So that's your hole current, JP. And that can be also taken from this image. So if you have holes moving from left to right, you will know that the current goes in that direction. So we are seeing here on the formula on a simple graph down here and by this formula. So when you have negative on one side and then this other negative, we know that it ends up being a positive current going from left to right. So let me erase some of these values right here. And now let's take the same example, but let's do it with electrons. So I'm going to erase this whole thing. So now, instead of magically adding or somehow adding holes to this piece of silicon, we're adding electrons. So if you add electrons to here, you have a bunch of electrons, E minus here. So you have a higher concentration here, and let's say you have a lower concentration on the other side. Those are the electrons that were already on the piece of silicon. And the electrons are going to move in this direction due to diffusion from left to right. But we know that by convention, the current is expressed on the opposite direction as the electric flow, or the electron flow, I'm sorry. So your current Gn will go from right to left, or we can express that on this same graph. But let's first go to the equation. The equation given to us for Jn Jn is equal to the same charge, the diffusivity of electrons, and the gradient of electrons. So on this graph, now you guys have the concentration of holes on this side on the y-axis and X on the x-axis. So you again have a higher concentration of electrons on the left side, and as you move along X, you have a lower concentration. And just similar to what we had before with the holes, we still have a gradient that's negative because you're taking the slope right here, so that's a negative slope. If you guys have a negative slope, that means that this whole thing, this thing right here, this equation is negative. So that means that even though you have a electron diffusion going on this direction, this is electron diffusion, your current is flowing on the opposite direction, just like we said in blue on top there. So for more formulas, one important thing to know about diffusivities, that's the dP and dN that we have in these formulas. So these diffusivities, we have something called Einstein's relationship. Einstein's relationship is used to find what those diffusivities are, or it's a relationship between diffusivity, mobility, and something else that we call thermal voltage. So it says this is equal to thermal voltage. So if you're giving one or the other, you can find what you're missing. What this thermal voltage is, or how it's represented, is like this. So this guy is thermal voltage, and is represented as Boltzmann constant times temperature over charge. So our room temperature at 300 degrees Kelvin, this BT is equal to 0.0259, and that's a number that's used a lot. So this is the overall thing that I have prepared for this section. So important things to remember: direct current is due to an electric field that's applied. Diffusion current is not. There's not electric field happening. It's just due to difference in densities, difference in the distribution of carriers, and the carriers go from high to low concentration. That's very important as well, and we're going to look a little bit more about that on the next video that's talking about